Okay, so hopefully this is what your three graphs look like from that roller coaster. Okay? Hopefully. Now, don't make this difficult. What I say is describe the shape. All you have, if you're a minimalist, all you have to say is that it goes up, it comes back down, it goes back up again. That's all you have to say, right? That's it. Don't make it complicated. So, the next question is the velocity constant? So, every motion that you've ever experienced in your entire life, it's only been one of two things. It's either been accelerated motion or constant velocity. That's it. There is nothing else in between. So, imagine that you're walking down the hall, right? And from a physics perspective, you see everybody in terms of like a vector, like sticking out of their chest, okay? And so basically, if they're walking in a straight line at a constant speed, that velocity vector isn't changing. Now, if they slow down, somebody's walking in front of them, okay? Hey, that velocity vector is going to become smaller. Then they speed back up. Oh, that velocity vector gets bigger. If they make a turn, you're changing the direction of that velocity vector. So if you're watching people and you see their velocity vectors changing, you know they're accelerating. If there's no change in those velocity vectors, it's at a constant velocity. Okay, so it's like a binary function. You're either accelerating or you're not. Those are the only two games in town. So when you look at this position time graph, and this is a function of logic. Okay, here's the position time graph. Okay, what does the slope of a position time graph give you?
Velocity.
Velocity. So if the velocity is constant, what has to be constant?
Slope.
The slope. Can you look at the graph? Is the slope constant?
No.
No.
So is velocity constant?
No.
So is it accelerating?
No.
Yes.
Yes. Bonus. Okay,
Hey, I was kind of in that rhythm, and then I was like, it took my brain a second to process.
that's my job. Okay, is like your brain to shift gears. Okay, so there you go. Now here's what I want. You're going to come out here to the 8-second mark, right? And I'm going to specifically give you time. So on the test, which is a week from tomorrow, I'm going to make you draw a tangent line. Okay? You're going to have to do this on the test. If you hand in the test when you get done on Friday and you have not drawn a tangent line and found the slope, you've done something wrong. Okay? I'm going to tell you straight up. This is one of the things you're going to have to do. So here's your line. You're going to go to 8 seconds, and here's what you have to do. You have to imagine that at that point, that's part of like a bigger circle, right? And here would be like the radius. And so you're going to draw this, and this is just eyeballing it. And you're going to come in here and you're going to draw this line, okay? Now, I think this is like 8 meters and 21 seconds. Yeah, 8 seconds, 21 meters. That's 8 seconds, 21 meters. You can use that as one of your data points to find the slope of the line. You can use that as one. But you've got to pick another point that's on this line. So what I want to see, because everybody's is going to be a little bit different, the only thing that I can grade you on is your process. So I want to see some number of meters minus some number of meters over some number of seconds. How are you not going to leave the slope? As a fraction. You know how I feel about fractions, okay? Frizzies, freshmen, there's a pattern, okay? Now, is this thing going to change direction? Just looking at the graph. As this thing approaches here, are you going to change direction?
Yes.
How do you know?
'Cause
What
velocity-
3 things do you have to do to change direction?
Slow down.
Slow down.
Stop. And speed up.
Speed up. So as you approach this peak, what are you doing?
Slowing down.
Slowing down. Then, when is your velocity going to go to 0? Very top. Because that's a relative maximum or a relative minimum. Okay? Or if you're a math nerd, when you take the derivative of this equation and you plug in that value of time, you get an answer of 0 because that's when your velocity is 0. So, you can have a horizontal line like this. Anytime you have a tangent line with a slope of 0, it's going to change direction. Okay? Guaranteed, it's going to change direction. Same thing is going to happen down here. You draw this tangent line across here, wow, there you go. So, you draw this line, I want to see the points. Then you're going to come over here to, what's the next one, 12? And then you're going to draw that tangent line. Again, you can use this as one of your points, but you got to pick another point on that line. So just looking at this, okay? Pretend that you're in a math class and you've got this line. Is the slope of this line positive or negative?
Positive.
Positive. What about the slope of this line?
Negative.
So here's the deal. Look at your answers. Guess what? The first slope should have a positive value. The second slope should have a
Negative.
And if you don't have a positive and negative, hey, something's wrong. Okay? Something has gone horribly wrong. So there's this one, right? So I should clearly be able to see 4 distinct tangent lines. One at 8 seconds, one at 12, one at 13, and the next 9. Okay? Everybody cool with what I want on that? We're good. Now, the problem is there's a little bit of variation. Great.
Oh, I forgot to ask, when you were talking about the slope and it can't be a fraction, like for example, I had like a number is meters per second, like it's always gonna be like a fraction, if you know what I mean, but like, is that fine? Like if I were to, can I write it real quick? Can I
Yeah.
show- Okay, so it's like, like 3 meters per second, that's the same as like that, but that doesn't count as being a fraction.
No.
Okay.
The unit, no, I'm just saying, here's what I don't want. I don't want you to say, oh, it's 4/3 meters per second.
Okay.
This is cool. Those are, your units have to be a fraction.
Yeah.
I'm talking about the numeric part of it.
Okay, alright.
Yeah. Yeah, you have to have the
Yeah.
units as a fraction. I'm just talking the number part. I just think you wanted it right on the board. Okay. Well, who doesn't? It's cool.
It's fun.
It is. You'll get a chance today, actually.
Okay, sweet.
I know, he's still my bidding partner. Okay. Just giddy with excitement. All right, so now, here's what you have to keep in mind. Here's the most common misconception that takes place. And that's comparing this graph to this graph. Now remember, this is horizontal position versus time. This is vertical position versus time. So here's what I don't want you to do. I don't want you to look at this graph and go, oh, the roller coaster goes straight, and then it turns right, and then it turns left again, okay? This is not looking down and seeing the roller coaster track. The only thing that I can tell from this is that here's the roller coaster. It's going to go forward, it's going to come back, and it's going to go forward again. That's the only thing that I can tell. I can't tell if it's turning left or right. I can't tell if it's in a loop. Not my thing, okay? So the only thing that you can tell, and that's a question, if you're looking down from on top, do not look at this and go, oh, it takes a right-hand turn and then it takes a left-hand turn. This is not the shape of the track. The only thing you know is that it's going forward, and then it comes back, and then it goes forward again. That's the only thing that you can tell, okay? Now, here's what's important in terms of the contrast. This is your vertical position versus time. Now, when this graph starts high, it goes down, it comes back up, it comes back down. When this graph is up here, that means the roller coaster is physically up here. When this graph falls, the roller coaster is going down. When it goes back up, the roller coaster is going back up. So, when you have this situation, thank you. Jones.
But
Here, go see the nurse. Get that done so I don't get interrupted anymore. Okay. So, you're here, down, up, down, okay? So, this, because it's vertical versus time, this is actually showing what this thing is doing. But if it's horizontal versus time, when you see a horizontal versus time and this thing goes up, that doesn't mean the car's going up in the air. You just know that it's going forward. Okay, so that's the most common thing that you all tend to get screwed up. Now, when you look at this position time, make sure that however you set up your scale, 2 and 2, 4 and 4, I don't care. Just make sure that you're using the same dimensions on each one. But this is only true for this one, okay? You don't have to have the same scales on the other one because you're doing time and position. That's why I only explicitly told you that in terms of this question. Now, let's talk about the very last question on the lab. So, here's what's important. Listen to me, listen to me, listen to me, listen to me, listen. I'm going to look for 3 parts of each answer on this deal. So you're gonna go between, what, 7 and, what's the first sign, 7 and 15?
15.
7 and 15. So you're gonna go between 7 and 15 seconds, and you're gonna look at this segment of this graph. And you're gonna say, wow, between 7 and 15 seconds, this is happening, okay? Maybe it's going forward, maybe it's only going forward, maybe you think it's only going backwards, maybe you think there's one direction change, okay? That's what you gotta figure out. So you're gonna say, horizontally, this is what's happening between 7 and 15 seconds. Then you're going to go over here to what's happening between 7 and 15 seconds. And you say, okay, between 7 and 15 seconds vertically, maybe it's only going down, maybe it's only going up, maybe it's going up and down. That's what you have to figure out. Then, once you get those two ideas, then you're going to go to the roller coaster itself and go, wow, which portion of the roller coaster will allow that to happen? Is it the loop? Is it the hill? Is it just going down the initial part of the hill? What is it? Maybe it's only the first half of the loop. Maybe it's the entire loop. I don't know. That's what you've got to figure out. Then you're going to do the same thing between 17 and 24 seconds. You're going to go out here between 17 and 24 seconds, and you're going to go, okay, horizontally, this is what's happening. Vertically, this is what's happening. Then, which portion of the roller coaster will allow that to happen at the same time? Okay? So on that last question, I want 3 parts to every answer. This is what's happening horizontally, this is what's happening vertically, and this is where I'm at the roller coaster. Okay? Honest.
Is it okay if I structured it differently where I said this is what happening and then use the horizontal and vertical to justify
Yeah,
that?
that's fine. As long as there's 3 parts.
Yeah, cool.
Yeah.
Thank you.
No
And will something like that be on the test?
In some form or another, yes.
Okay.
Yeah, in some form or another, I promise. Okay. It might be a gazelle chasing a lion. I don't know what it's going to be, but yeah.
That'd be an interesting graph.
Or a lion chasing.
Okay, lion chasing gazelle. Whatever.
No,
Don't bandy words with me.
this is Bergkamp's dream. Let it be what it wants to be.
Let me dream the dream. Okay. Anything else? Once, twice, yes?
First, a hypothetical question.
Hypothetically, okay.
I mean, okay, I didn't do this, but what would the graph look like if the 2 position graphs look like if you didn't put it to scale?
What do you mean?
Like, to use the same increments, what would it look like?
Like if you had the same increments going both ways?
Oh, no, for the position one, yeah.
If you didn't?
If you didn't.
Well, typically what would happen is that you're going to, like, if your vertical scale is bigger than your horizontal, then your loop would look like this, okay, and it would get stretched out vertically. Or you'd get a situation where it would stretch out horizontally, and it would get something like that. So you would just get a distorted shape to the graph, that's all.
I want to ride that coaster.
Which one?
The one that goes.
That'd be fun. You get some airtime.
Oh, yeah. Okay,
Airtime.
anything else? Are we good? Once, twice, sold? So stop that. So here's what we're going to have. I emphasize the word informal, okay? An informal quiz. You're not going to hand it in. It's not for a grade. I'm never going to see this, okay? So you can even have frizzies on the side. You can do this in pen. You can do it in highlighter. I don't care. Okay? It's an informal quiz. So what I've got up here is a fan card, okay? Does it have a card and it has a fan on it. And it actually puts out like a decent swing of air, okay? So we got this up. Yeah. Okay. So here's what's going to happen. I'm going to go back on the floor. I'm going to put this down. And I'm going to let go of it. And we're going to let it roll, okay, until Hunter stops it, okay? The floor. So now, here's what's important. The fan is going to be spinning at full speed when I let go of it. Okay, so I'm not going to turn it on, let the fan speed up and the cart speed up at the same time. I'm going to have this revved up at maximum force. I'm going to let go of it, and we're going to observe what's going to happen. Okay? Then I want you to draw a position time graph and a velocity time graph that describes the motion. Okay? So, come back here. So, stand up so you can see it. Okay?
I'm just taking your spot at every turn. My apologies.
Okay, so the fan's already at full speed, so I'm going to let go of it. Now, you're going to start the observation as the second that I let go of it. Okay? So I'm here, right? Now, here's the other thing we need to decide. Oh, the anticipation is killing me. What do you want the reference point to be?
You.
Well, that was simple. Do you want the positions going that way to be positive or negative?
Positive.
Okay, so we're starting at the reference point. We have positive positions going forward. Okay? All right. So kick the tires and light the fires. And here we go.
Oh.
Okay?
You broke it. You told me to stop it. You stepped on it, man.
You idiot.
You broke it. You done did it. Oh, there it goes.
You brought it back to life. Okay, so do it again. Seriously. Okay, we'll do it again. Okay. So we're at full speed, right?
Kill it again.
We let go.
There it is, Brian.
Wow. Okay, now we're not including the stop.
Okay.
Okay, we're not including the stop.
So we're assuming it's continuing.
Yes. Now the other thing that we're assuming is that it doesn't reach like its maximum speed. Okay, it does not reach its maximum speed because it will eventually. I mean, if I let that thing go long enough, it's not going to break the sound barrier. Okay, or the speed of light. Okay, it will eventually like max out. So here's what I want. I want a position time graph and a velocity time graph to describe that motion. Okay? Make it happen.
Can it be a rough sketch or do you need?
So, here's the rule. Keep it. Go.
It's gone.
Okay. So, when you have a graph drawn and you're feeling good about it, come up here, either draw the position time graph or the velocity time graph. You cannot do both. If someone has drawn a curve and you think you have something different, come up here, draw that in a different color so we can know which one is which. Okay? So, you're going to draw either the position time graph or the velocity time graph up here. Now, on the velocity time graph, here's 0 meters per second. I've given you both the positive and negative region. You don't have to use the positive and negative region. I'm just saying if you do, you have both regions to go from. Okay? So when you think you have it drawn, if you haven't figured out, come up and draw one of them. Great. Whew. First one out. Huh?
Is it this?
Really? That
Because
is
at some
okay,
point the
man.
velocity will.
Pick one.
No, but it was starting to slow down a little bit near the end.
Yeah, it's
Nick, quit flipping birds.
Are you serious, man?
That's so rude.
That's such a soccer player thing to do.
It really is.
Grass fairy. Yeah, I did.
Okay.
Go, Max. Do it. Oh, Max.
Now, if you have something different, draw it in a
You do
different
have a
color.
different position.
Yeah. I have the correct thing.
Max, go for green. Go for green.
Oh, yeah? Yeah.
I agree, Max.
Wow, I did, Max.
I second that.
Okay. Oh, Mary!
She's gonna
Proud
be
Mary keeps on rolling.
wrong. You might do it, but
All
you're
right.
getting wrong.
There is no purple.
Isn't that the name of the song, There Is No Purple? Isn't that sad?
We're not including the stop.
What?
Oh wait, no.
Oh, oh, Olivia, come on.
Mix colors to make a purple?
Huh?
Do you think I could mix colors to make a purple?
I don't think it does color blend.
Oh,
Oh,
Mary, you weren't inventive enough. You weren't inventive enough to find purple.
we could have done a dirty brown.
Ew.
Yeah,
Okay.
I agree with that. I'm happy.
Does anybody else?
Greg got a little excited because he thought he was matching with Hunter.
In terms of what?
Shirt,
Not so?
not so.
Different brands.
Different brands.
Awkward.
Very.
Another soccer player
Okay.
thing to do.
Hey, shut up.
Too many headings. Okay. I have name brands. Okay. Anybody else have any
Ah,
other
dang,
line drawn? If I went and looked at your papers, these are the only possible 4 lines that I would see.
Yes.
There is nothing else there.
I mean, there are a lot of possible lines, but I don't think anyone drew them.
Really? Let me see. I don't have my glasses on. I can barely see the holding paper.
I like Mary's graph.
For which one?
The velocity time graph.
I like the one.
Draw that.
I feel like Max is like really neat.
So,
Jeez, Max. Maximina, calm down.
She's saying
Maximina?
selection is decreasing, if anything.
okay. What?
Max is very passionate about his
Maxamina's
work.
getting angry.
About which one?
About the velocity time.
Yeah.
Olivia.
They're what?
Yeah,
Do you have another one that you want up here?
What?
No,
Well,
he's
no, I just,
he strongly believes in the purple one.
Yeah,
This one.
I believe that one is the most, I believe that one is the most correct.
Okay. All right. So there is no other line on any of your papers except for what is up here. There is no one has any other line. Oh, Michael!
Yes, Michael.
Okay.
I have a rationale for this.
Okay. That's interesting. Okay. All right.
Second one.
Okay. No one else has anything else? Okay, good. All right. Now, let's start with what we saw happening. Okay? What did the cart do?
Sped
It
up.
moved, right? It moved. Everybody agrees it moved.
Did the
Yes.
card move or
Nice.
did the world just spin?
Or yeah, or was the cart stationary and the earth moved out from underneath it?
Well, we chose you as our reference point, so the cart moved.
Huh?
We chose you as the reference point, so the cart moved.
Okay. But I can be part of it. Yeah, what, that'll look good on a college application. The earth moves around me, I am the reference point. Okay. I was voted most likely to be a reference point by my high school class. Okay. That should be a criteria. Okay. So, now let's talk about this. It moved, assuming that the earth, that it moved, okay, and wasn't stationary. So, it moved. Did it speed up?
Yes.
Yes.
Yes. Okay, it sped up. Everybody is agreeing with that. So let's start with the position time graph. Okay, so grape,
Yeah.
right? You drew a straight sloping line on the position time graph.
Did.
You did. Okay? So what does a straight sloping line on the position time graph indicate?
Means there's a constant velocity.
There's a constant velocity. Is that what happened?
Felt so. I mean, I felt like it was going the same speed. Okay, so it eased
Do we
into
need
it,
to
you're
review
right.
the tape?
So it actually, it kind of went like that, and then it had a straight slope. That's what I think.
Okay, now, what did I say? What did I specifically say? Did it reach its constant velocity?
No.
I specifically said it did not reach a constant velocity.
I think I missed that part.
Okay, so, but I'm going to leave this up here because here's the deal. If Grape's line is right, that cart was just, what would have happened is that it was moving at a constant speed the entire time. Is that what happened? No. Okay, all right. But here's one thing I want to point out. Let's assume Grape's line was right. Let's assume that this is right. It's not, but let's assume that it is. So if this is a straight sloping line, which line over here corresponds with a straight sloping line on a position time graph? Michael's does, right? Because Michael's agrees with Grape's line. Because Michael's line says this thing is moving at a constant velocity the entire time. Okay? So this matches this. Okay? But now, let's say that we have the green line. So everybody cool with the green line?
Yeah.
Why the green line? Who drew the green line?
It gradually.
Max. So what does the slope of a position time graph give you? Velocity. So the tangent lines are becoming more and more steep, right? So what does that mean? Speeding up. Is it accelerating?
Yes.
Yes. Is it going faster?
Yes.
Yes. So let's look at this spaghetti plate over here. Okay? So who had the purple line?
I thought you meant who agreed with it.
No. All right. Now, Olivia, what was your feeling on drawing it like that?
Because the slope increased a lot at first.
Okay.
The other one, so that means the velocity is increasing a lot, so it should be like really steep. And then it stops increasing as much on the position time graph, so then it kind of looks.
Okay. So you're saying it's going to speed up real quickly and then not so much.
Yeah.
Okay. Now, who drew the red line? Okay. Great. What was your feeling on that one?
No, honestly, there's
No. Keep going.
I threw it out there because I figured someone has to have a stupid one out there, so.
And then you took one from the team.
No.
Okay.
No, that's not the answer, Nick.
Alright, so I thought it was accelerating like consistently upwards.
Okay.
I mean, not consistently, but I mean, I thought it was gradually,
Going faster, faster,
exponentially,
faster.
yeah,
Okay.
yeah.
Right. Now, what about who drew the first green line? Okay, Mary. What was your thought process?
Well, I thought that it would speed up at first, but not for very long, and then
Yeah.
it kind of level out.
So this would indicate a constant velocity, right?
Yeah.
So did it ever reach constant
No.
velocity?
But I missed that part.
Okay.
So that it's accelerating,
Wait.
increasing.
If it's any consolation, none of these are right. Okay?
Ooh.
Now, and I'll tell you what. You all, does anybody here have anything with a Nike emblem on it?
Oh.
Yeah.
Yeah.
Okay.
I got
nice.
socks.
Right. Okay. Here's the deal. I blame Nike for all of these being wrong. Okay? This is Nike's fault. Because look at the Nike swoosh, right? What do you associate movement with? Oh, the Nike swoosh, right? Ooh, we have like curved lines, right? Okay? That's what you associate. Notice that we don't have the Nike stick. Okay? That's cool. Look, it's the Nike stick. No. Okay?
It's Adidas, he said.
Yes, okay. No. We're talking Nike here. Now, so this is where you look at this in terms of a grander idea. You're confusing acceleration with an increase in speed. Okay? At its core, acceleration is the rate at which your velocity changes. Okay? Now, here's the deal. Pretend that doesn't exist, and we're going to look at this. That big sign hanging up in the back, F equals ma, right? So, what does the m represent?
Mass.
Mass. Do you think the mass of the cart changed?
No.
No, it isn't like we dropped an elephant on it halfway through. Okay? M is a constant value. What was providing the force?
The fan.
The fan.
Wind.
This is why I had the fan spinning at a constant rate. Okay? So when the fan was spinning at a constant rate and I let go of it, did the force remain constant?
Yes.
Yes. The force remained constant. So if the force remains constant and the mass remains constant, guess what? The acceleration has to remain the same. Huh?
But then you just say it remains constant, like the speed of it.
Yeah, it is.
Oh, it's the velocity.
So I said the velocity never reached a constant point.
Okay.
So it never reached like its maximum speed.
So that has nothing to do with this equation.
No. So how can I show the same acceleration happening all the time on this velocity time graph? Yeah. This graph needs to be this. Did you have that?
Oh, yeah.
Yeah.
I asked you. Does anyone have anything else? Did you draw that? That was well deserved. Okay. Now, so here's what your velocity time graph should look like. And it's boring because you're going, oh, but Mr. Burkamp, it's going faster. We need swooshes, right? Because that's what indicates that it's fast, the swoosh, right? This is boring. But this is the reality of it. Because you're associating acceleration and speed, and they're not the same thing. So all this is saying is that in each interval, my velocity is changing the same amount. Now, in reality, what is this velocity time graph eventually going to do? If I let it go long enough, yeah, eventually this thing's going to level off. I'm not going to break the sound barrier with this cart, which would be cool, okay? But it's not going to happen. Eventually it will level off, right? Now, if I were to find this area right here,
Yes.
physically, what would that represent?
Displacement.
It would, but physically, what would we have measured?
How far the car went.
Yeah, we would measure how far the car went. So if we measured the distance between where I let go of it and it got stopped and broken, then whatever that distance is, that's what would be the area underneath this line. Because this area represents displacement. Okay. Good with that. Okay, now we're going to do this again. So, get ready for a second observation. No need assistance. Well, I'm good. I don't need anything on this one. Okay? Now, listen to me very carefully. Do not include the push. Okay, because I'm going to give this thing a push to start it. Do not include the push. We're going to start it as soon as I let go of it and right before I stop it. Okay? So, what?
Do you want me to get action shots?
Yes.
Okay.
So, listen to me. Do not include the push. Do not include me stopping it. The point that I let go of it is the reference point. Okay? Going away from me is positive positions. Do not include the push.
Okay.
Okay? All right.
Yes, sir.
Gotta get this bustling camera.
Whatever it goes.
I explained that first block. What did they do?
Including the push.
Okay.
But their first block. You said first
Okay.
Mary.
All right. So we're up to speed, right?
I'm sorry.
We'll do that again.
Okay. So it's from the point that I let go of it until right before it gets back to my hand. So I'm here. And I'm here. So this is the reference point. What are you not going to include?
Or the stop.
Or the stop. Okay. So again, I want a position time graph or velocity time graph.
Are you still recording? Yes.
Just gonna have to edit that out.
Stop that. Just because. So
What color would you like?
it's up to you. It's your line.
I like it blue.
I'm just the casual.
periwinkle.
Okay?
You scare me.
No, you're good. Vonda, help me, Vonda.
I looked that up, and it's Rhonda, not Vonda.
I know it is. That's the humor in it. Whoa. Okay, that's aggressive. Wow,
Let's go, Hunter.
with authority. There you go, big man.
I feel like
Yeah.
Woo. Okay. That's aggressive.
well,
Oh, Homies is having pause.
We ponder this for a few years.
I mean, it did have a
Or a
change,
few beers.
because it did have a change in direction.
Oh, I prefer the second option.
Give me a second.
If you have anything different, Shively? Both of
Because it
those
had a change in
look good.
direction.
Really?
It started up the top, yeah.
Really?
It started with the nice velocity.
I would say maybe a little plot twist in this, I feel like.
Huh?
So would you say it's kind of like this?
No one has anything else on their, what?
I have a thought, but I don't know.
I don't like this one.
Okay?
Don't be afraid to do wrong.
Because we don't.
Okay, Matt, you haven't gone up here to get
And like
No, we
this.
don't include the push.
You do not include the push.
And the
Did
reference.
we not establish
I
that?
know.
So,
The reference point is you.
The reference point is, where I
would
let
you
go
agree
of
with this then, Max?
Yes. So when that, if you
Because-
don't include the push, it starts away from the reference point.
Yeah?
No, it's like, we're
Do you
making
think
the
that's
reference
right?
point, that exact point that
No.
it leaves my
I'm
hand.
just saying.
That is the reference.
Matt, what'd you put for velocity?
The reference point, no, actually,
What'd you put for velocity?
it's where he lets
Yeah,
go.
that's what I'm thinking it is.
What are you doing?
Just like a tile.
But-
right?
Oh, okay.
Why does it go
Draw like
positive? It
a
doesn't go
line.
positive
Okay.
because you can, if he's not stopping it,
Yeah,
it would
so
just
it
go.
stopped right there.
But he's not stopping. He's don't include the stop. So as if it were to keep on
It's gonna be
going.
smart for a second.
Turn
Here we go.
But it doesn't ever go positive because it's always going in negative direction.
Which one are you gonna do?
Velocity was going because it went like this and then changed direction. Now do you see what?
But it's,
But velocity can be negative.
yeah, I know that. So it doesn't go past.
Well, it would go past it.
No. It wouldn't come back up.
Yeah, but it would come back up, but it doesn't go like this and then just keep on going down. Yeah.
Okay.
I think it might flatten out at some point. No.
Yep.
No.
He's only German.
I've got German, and then maybe sometimes a little bit of a northern accent, just because that's where my
Everything's like, yup.
Yeah, so many things can be.
Okay.
Just white.
Does anyone have anything else to draw?
Wait.
Hey, what?
Wait. Even if I've already drawn.
Now you're drawing.
Okay, good. I don't want to embarrass myself.
Now you can send someone up on your behalf.
I'll do it, Eric.
Don't, no.
I'll go for
No,
you.
you go. No, you do your own idea. I don't want mine up there.
Well, she didn't.
Eric, let me put your idea.
No.
I know what his idea is. I'll put it
Okay, all right, come on, Matt.
Matt, you stop.
I'm
No.
gonna steal my idea.
I was right.
Go, Logan.
I don't know.
Okay.
Does that look good, Eric?
Sure.
Hey,
Redo it.
I think
No.
I have a different one though.
Max, go put it up there.
Go,
Dude,
Matt.
I'm concerned that it's not bright.
Max,
Logan's scared to look like an idiot, so there you go. Good night to me now.
There we go.
are you going up there, Max?
I'm dying.
Is that the girl?
Just think about it.
Okay. Anything else? Okay.
Is at least something up there right?
No.
Nothing.
One line is right.
Oh,
Out of all of this.
is it mine?
one line is right.
I bet it's
The rest of them are
It's totally
Okay?
I hope so.
So again, let's start with what happened, okay? Was the initial velocity of the cart, when we started the analysis, 0?
No.
No, the cart was already moving. So should any of the velocity time graphs start at 0?
No.
No! So right away, if this starts at 0, you did not listen to a word that I said. Okay? I said, don't include the push. Okay? Don't include the push. So, okay?
The push means it started. Nick.
No, seriously.
Okay.
Think about it.
If you include the push.
But I said,
I mean, if you don't include the push, then
it's already moving when we started the analysis then.
Because it's already at a velocity relative to the reference point. It's moving away quickly.
Yeah, it's moving past the.
Yeah, because like where he let go of it is our 0 for time. So it's like still moving.
Okay. So, everybody agree that this position time, or this velocity time graph needs to start somewhere up here.
Yes.
Okay, good with that.
I'm halfway right already.
Now, on the position time graph, did it return back to the reference point?
Yes.
Did it go past the reference point?
No.
No, I stopped it right where I let go of it. Okay?
But we don't include the stop.
Let's stop it right when it gets back to where it started. So your shape is right, just don't do this. Okay? Now, for the most part. So here's the deal. As soon as it left my hand, what did it start to do?
Slowing down.
Slow down, right? Now, Vonda, you had a straight sloping line on this position time graph.
Yes,
What is indicated by a straight sloping line on a position time graph?
a constant velocity.
So here's what would happen. If your line was right, this would be cool to watch. And I'll tell you what. I would push it, and it would move at a constant velocity the entire time. And then all of a sudden it would stop, and then on the way back it would start slow, and then it would speed up as I got back to my hand. Yours would be cool. Okay? Because I'd let go and go like this, and then it would suddenly start, and then it would speed up as it came back. Is that what happened? No. So the second half of your curve is good. The first half, not so much. Okay? So this purple line is right. Now, blue line, whatever. Okay, don't make me work. So here's the deal. It's right because you have the steepest slope, and then it breaks over center, changes direction, and then starts to speed back up. So this is this line right here. So the position time graph should be a pretty quadratic line like this. Okay? Can't be linear because it was always speeding up and slowing down. Now, let's start with this. Based upon this position time graph, and here's the biggest thing, both graphs have to show the same thing happening at the same time. So if you go to time 0 and you draw a tangent line, this thing is going to start with a positive velocity.
It was Riley Baden. He looked at it and was like,
Okay. So you got. So here's this is where both graphs have to show the same thing happening at the same time. So if this starts with a big positive velocity here, that means my velocity time graph has to start up here with a big positive velocity. Okay?
No, I'm halfway.
Okay.
I'm taking partial
Partial
half.
credit.
Yeah.
Partial.
Yes.
Now, up at the top, what's the velocity?
0.
Why?
stop.
Why did it stop?
Because it has to change direction.
Beautiful. Okay? Now, afterwards, what does it begin to do? So, this is the 3 criteria. It has to
Slow
slow
down.
down. What's happening here? Stop and speed up. So, how can I show it with this? Here's 0 meters per second, right? So if you go back, who had this dip-de-doo?
Well, those are
That,
two
that
different
two different
lines.
lines. One's red.
So
One came down
I'm
and-
no. One of
The one that goes back
God.
up starts at 0.
Yeah. So
Okay.
only the second half of it is
This one?
correct.
Yes.
Okay,
that's fine.
okay, well, let's talk about whatever line this is, this one, right?
Yours is a pink one.
Does this one show a change
Yeah.
in direction?
Yeah.
It's just two.
No, why?
It doesn't
Doesn't cross
cross
there.
It doesn't cross through 0 meters per second. So this one starts slow, speeds up, slows down, stops, and then keeps going in the same direction, which would be cool. So I would push it, it would start slow, speed up, slow down, stop, and then continue on in the same direction. Cool, not what happened, okay? So the good news is that everybody else crossed through 0 meters per second. True? Okay, that part's cool. So now let's talk about this blue line. What's indicated by a horizontal line on a velocity time graph? Constant velocity. So is this line consistent with the parabolic curve over here?
No.
No, why? It was a constant. So if you see a curved line over here, you cannot have a horizontal line over here. Okay? They're not, so what would happen, this would be cool, I would push it, it would move with a constant velocity, all of a sudden, whoo, it's going to slow down. Okay? Right when it got to the end, stop and then speed back up. And then I don't know what happens here. Okay. So is this what happened? No, it did not have a constant velocity for the first half of the trip. It started to slow down as soon as it started. Okay. Now, let's go back over here. On our velocity time graph. So do you all agree that it has to cross through 0 meters per second?
Yes.
Okay. Now, do you all agree it started with a positive velocity?
Yes.
Did it end up with a negative velocity?
Yes.
Everybody cool with that?
Yes.
Did it accelerate?
Yes.
How do you know? It changed direction and it was speeding up and slowing down, right?
Yes.
Okay. Did it ever have constant velocity?
No.
No, it was speeding up and slowing down the entire time. Now, one of the things that you can do is you can look at this from a vector standpoint. So here's the cart, okay? Right? Fan cart. So it started with some initial positive velocity. So here's like this initial positive velocity vector. Don't worry about the scale, it doesn't matter. But as this thing rolls, this vector can do one of three things. It can either get bigger as it rolls, indicating that it speeds up. It can stay the same, which would be constant velocity, or it could get,
Slow.
which one did it do?
Smaller.
Small. So if this is V1, then over here, you're going to have like a smaller V2, and then you're going to have an even smaller V3. Everybody cool with this?
Yeah.
Did it accelerate?
Yeah.
Okay, once you establish that it accelerates, your acceleration vector has to point in one of two directions. Your acceleration vector is either going to point in the same direction as your velocity vectors, or it's going to point in the opposite direction. So which direction is it going to pick? Why? Slows down. Because if something slows down, what do you know about velocity and acceleration? They're opposite signs, right? So if I have positive velocity, I have to have, so I'm going to make my acceleration vectors be a negative number. Okay? Negative, negative. So right away I start with positive velocity. Is this line going to slope up or is this line going to slope down?
Slope down.
Because I'm going to have negative acceleration. Cool with this?
Yes.
Beautiful. Now, at this point it's going to stop and now it's going to roll back. Olivia, once it starts to roll back, what am I going to do with my velocity vectors?
Flip them around.
And make them
And then
either bigger or smaller as it goes across.
make them bigger. as it goes.
Because it's going to be gaining speed as it comes back towards me.
Yeah.
Right? Okay. So now I'm going to have negative V1, a bigger negative V2, an even bigger negative V3. So here's my question. My velocity vectors are getting bigger in the negative direction. speeding up. So what's the sign of my acceleration? Negative. Oh. So do you think the negative acceleration vectors to make it slow down are the same as the negative acceleration vectors that are going to make it speed up?
Yes. Yes.
Wait, say that again.
Okay. Are the negative acceleration vectors that are making it slow down going to be the same as the negative acceleration vectors that are making it speed up?
Yes.
Why?
Because it's F equals ma. It's the same force that was
F equals ma,
acceleration.
right? So F equals ma. Did we change the mass?
No.
Did we change the force after it left my hand? No. So I've got a negative force acting on a positive mass, so what's the sign of my acceleration?
Negative.
Oh, negative. So how can I show the same acceleration happening on that velocity time graph? Ethan gives the international sign for, oh, uniform acceleration. That should be the line.
I was somewhat close.
Okay? And again, you all are victims of Nike. Here's what you go back here, you all want to believe the curved line. Okay? You want to believe the curved line is true. Oh, but it's slowing down and speeding up. We must have curved lines. No! Because again, what do curved lines indicate on a velocity time graph? What's changing?
Acceleration.
Your acceleration. To change the acceleration, you'd have to change the force. Did I change the force?
No.
No, it was the same propeller spinning all the time. It's boring, okay? This is boring, but guess what? It's right. It's right, okay? Which happens a lot of times. Sometimes what's right is boring, okay? Like driving the speed limit, boring, but guess what? You don't get speeding tickets. Okay, now, if I were to find, I'll change up the color a little bit, we'll go with the purple, okay? If I were to find that area, what would that represent? Physically, what would it mean?
Since it travels away from you.
How far it goes away from my hand to where it stops. Now, if I were to find this area, what would that mean?
How far away?
Where it stops to
From where it stops to
You.
where it gets back. Now, trick question. If I were to add this area to this area, what do you think I would get?
total displacement.
Which would be?
Zero.
Why?
Because it went from the reference point away
Because it
from
returned back to
the reference point.
the starting point. So, does this boring line show the three criteria for a change in direction? Because what's it doing here? Nip. What's it doing here?
Change or like going in the negatives?
No, just that black line. What's it doing? Speeding up or slowing down?
Slowing down.
Slowing down. What's happening when it crosses here?
Change directions.
No.
Stop it.
Stopping. Then it's going to
Change direction.
and
Speed.
speed up. Now, sometimes kids will bring in like this, and then they'll take that up as a V. This would be cool. If this was the actual line, what would the cart have physically done? Slowed down, stopped, and then when it would have like kicked in the rocket thrusters, okay, and then would have kept going in the same direction, which would be cool, but they frown on rockets and buildings. Okay. Everybody kind of see what's going on?
Yeah.
Maybe.
Okay, maybe?
I understand.
A little better?
Yeah.
This is why it's an informal quiz and not for a grade. Okay, so stop that, and then start that, we've got me. Or if you've never stopped.
I did start it.
Okay, so let me go through like a number one. You want to use the word while. I said, what's the difference between a scalar and a vector quantity? You want to say a scalar quantity has da-da-da-da-da, while a vector quantity has da-da-da-da-da. Okay? Got some questions to answer? When you get to number 5, let's talk about number 5. Number 5 is brought to you by this equation, distance equals velocity times time. What's the only situation in which you can use this equation? One specific, unique type deal. Accelerated motion or constant velocity? Constant velocity. And here's the reason why. Because if you're accelerating, what's happened to your velocity? It's changing. So if you're accelerating, you don't know which velocity to put in here. Okay? This is a beautiful equation. You all have done this for years. But here's what's important. You can only do this if this is a constant velocity situation. Now, let's talk about number 5. You've got 70.0 kilometers per hour. How many significant digits are there in 70.0? 3. Now, do you think you're going to leave that in kilometers per hour? No. What are you going to change it to? Meters per second. So don't forget, if you've got 70.0 kilometers per 1 hour. 1 kilometer is 1,000 meters. We've been over this. 1 hour is 3,600 seconds. The zeros cancel out. The shortcut version is you multiply by and divide by 36. So multiply by 10, divide by 36. Now, listen to me. When you do like a subconversion, when you're taking that 70.0 kilometers per hour and you're changing it into meters per second, 70.0 has 3 significant digits. At a minimum, when you change that into meters per second, you want to keep at least 3. It's better if you keep like 4 or 5 because you want to carry more digits in your subcalculations and then round when you get to the end. Okay? So, when you convert that 70.0 into meters per second, at least have 3. I prefer 4 or 5. You don't have to have all 10. Okay? I don't want you to write down 3, 4.325, whatever. Okay? Okay? But just kind of have some reasonable opinions on it. Now, you've seen this. Now I want to give you a different perspective on this. Okay? So let's say that Hunter is running at 8 meters per second, and he's going to run that way for 5 seconds. Okay? He's running at 8 meters per second for 5 seconds. How can I draw this on a velocity time graph? What would that look like? Running 8 meters per second for 5 seconds. Barry, what was this? Was this or this? Slope climb. So here's your velocity time graph. Is it up, horizontal, or down?
Horizontal.
At?
8 meters per second.
I like how you had like the fingers going. That was nice. Okay? 8 meters per second. For how long?
5 seconds.
Looks like a rectangle. If you're a geometry person, and this is it's a little bit weird, but you can handle it. If I gave you a rectangle, how would you find the area of a rectangle? Length times width. Oh, you would go area equals length times width. True? So if you look at, now what does the area on a velocity time graph give you? No, the area. Displacement. Oh, so look, if you look at distance equals velocity times time, it's like an area equation for a rectangle. The area is your displacement, the length is your time, and the width is your velocity. So from a pure mathematical standpoint, this is giving you area, which is the same thing as taking length times width. Okay? So it's the same idea. I don't care how you view the problem, just pick one. Okay. Now, when you get to number 6, listen to me on number 6. Listen to me very carefully. Here's the setting. Here is a tree, okay? Tree of life. We're going to make this the reference point. We're going to call this point A, okay? Here's point A. Here is the bicyclist. He's riding a bicycle. That's why we call him a bicyclist, okay? So he's here, right? Where is he? And if you look, read the problem. He is starting 250 meters away, 250 meters away from the reference point. He is not starting at the reference point. He is 250 meters away from the reference point. Okay? Here's the reference point. He's not there. He's way over here. Okay? Now, which direction is he going to be going? Away from the tree or towards the tree? Away from the tree. How do you know?
Positive acceleration.
It's got a positive velocity. So he's going to go away from the tree for 30 seconds at 5 meters per second. Okay? Then he's going to realize, oh, dude, I left my Scooby-Doo, lunch container back underneath the tree. Oh, I can't lose Scooby-Doo back there. So he's going to turn around and he's going to go all the way back to the reference point. So he's at 250. He's going to go away. Then he's going to go back. Now, is he going to change direction?
Yes.
What does his velocity have to do?
Change sign.
Change sign. So his velocity is going to become a negative value. That's why that's negative 10. So he's going away at 5, he's going back at negative 10. You're going to draw a position time graph, okay, for the first 30 seconds, and I tell you how to lay this thing out, okay? That's one graph that you're going to have to draw. And you got a whole series of questions to answer about that. When you get to number 7, 8, 10, and 11, all of those are going to be based on this equation that displacement equals velocity times time. You're going to use that on all of them. Okay? You're going to use that on all of those. In all of those, I've given you 2 of them and asked you to find the 3rd. Okay? And all of these are constant velocity. They're not accelerated motion. When you get to number 12, 12 is a position time graph. I'm going to keep in mind it is a position time graph. Okay? And I'm going to say, hey, did they change direction? How many times? How do you know? Was it ever constant velocity? When you get to 13, 13 is a velocity time graph. I'm going to ask you some questions. Now, when you get to 13E, pay attention to 13E. For whatever reason, y'all tend to skip 13E. So, I got using arrows indicate if the object is slowing down or speeding up in each segment. So let's look at the beginning of this graph. So you got some action going like this. This is a velocity time graph. What are you doing from here to here? Speeding up or slowing down?
Speeding up.
How do you know?
The slope is increasing.
Well, where are you starting at?
0.
Can't go any slower than 0. So what do you have to do? Speed up. So you're going to put an up arrow indicating that you're speeding up. If you're slowing down, put a down arrow. So don't forget 13E. Okay? Yes?
On 13, when it goes straight across,
Yeah.
do we have to put an arrow for that? Or
No, because
it's not
if you
doing anything?
you only put arrows if it's speeding up or slowing down. If it's not speeding up or slowing down, there's nothing to put. Okay? We're cool. All right, Matt, shut that down.